Swayam Prabha. Digital India. Educated India.
So hello all of you. I'm extremely glad today to show you one wonderful case study, a collaborative innovation across multiple departments, across multiple agencies and across multiple organizations. So this is one wonderful case study where we can learn the design, which doesn't necessarily need to happen with designers. Even surgeons can design, professors can design, manufacturers can design, right? We saw that happening earlier. So whereas there's design, there is research and technology. We only talk about technology in our course, but also there is research, right? Ahead of technology, there's research which comes and, embeds into technology, and, from research, you have technology to application, right? All those happens. And of course, there is innovation, where the major hallmark of innovation is that it has to reach the people at large, and then only innovation is said to have happened. Otherwise, we say that it's just an innovative idea or innovative research or innovative technology. So those are the three, important aspects which keep happening. So this mega prosthesis is a, knee implant for children who are, suffering from cancer of the knee. And here, for example, if you don't have this mega prosthesis, the doctors have to ampute the leg. So this is a very, very interesting sort of project. I'm very fortunate that I was not the core team, but I was a support team here in innovation, where I was, working with the core team of, professors and doctors and manufacturers, where I would invite Professor B. Ravi later on to show you how this whole journey unfolded. So right now, just to leapfrog directly into the activity, let me show you this film which completely captures this complete scenario, so that you understand the complete scenario, and then Professor B. Ravi will come in and he will talk to you about what happened behind this, how much of research happened, how many students and professors worked on it, what type of implementation happened, and currently where it is. So till that stage, we will have Professor B. Ravi from our mechanical engineering coming and explaining to you.
Tata Memorial Center is a part of the Department of Atomic Energy, and you need mega prosthesis implants, and one of the crucial ones is in the knee. So we decided to bring together Dr. Agarwal, who is interested in this, but then we wanted a good mechanical engineering. That's why we got Dr. Ravi from IIT Bombay, and it was very clear that it has to be a non-ferrous metal alloy design. So we brought in the NFTDC from Hyderabad, Dr. Balasubramaniam. And this is an excellent example of how people with different competences can work together and then create a world-class product.
When Dr. Manish Agarwal had met Dr. R. Chidambaram, the principal scientific advisor to the Government of India, and that is when he shared with Dr. Chidambaram the fact that he had a wonderful idea of a project with a lot of societal implications.
Bone cancer had become curable with the chemotherapy. After he is cured of his bone cancer, the only problem that remains is going to be mechanical or prosthesis related. So we needed an Indian prosthesis which was high quality but which was still affordable to our patients, and that started our need.
So TKP is not just one product. Actually, it is a system of products. We have the main device in multiple components. Then we have surgical instruments, quite a number of them. And then we also later built a walking machine to test the joint for millions of cycles to make sure it is safe before human trials. Now the first versions of these were developed in AutoCAD lab in IIT Bombay, and later on they were taken over by NFTDC Hyderabad.
We are making it by state-of-art computer-controlled processes using very high-quality materials and elaborate testing mechanisms both for the input materials as well as for the final product. Above all, it has been tested in a knee simulator testing machine for over 10 million cycles. We are very confident that it would be superior product and it would restore much of the natural functions of the knee joint.
Our Indian patients, they will get the best possible implant and the best possible treatment at almost 1/4 the cost of what they have to pay for getting this important implant in their body for such a serious condition such as cancer.
The good part of this project is that every 3 months we had a very sincere, devoted type of meetings for the development of the prosthesis.
After the year 2012, there were a lot of changes in the guidelines and the law regarding the clinical trials, and I had been giving inputs regarding those.
It was a marvel of engineering which was to be implemented in human body.
We were able to develop further team of next generation of scientists and engineers. So a large number of youngsters in design, in manufacturing, in materials, and even junior surgeons.
We're looking at how we could redesign some of the armamentarium which is used to operate upon and put the process in the human body, as well as work on the packaging and making the whole product and the processes very user friendly and convenient for the doctors, as well as convenient for the systems to take this thing forward.
The seed of AutoCAD, the TKP project, which was sown in 2007-2010 with the first phase of the project, has now grown into actually a big tree with many branches. This tree, BETIC, or Biomedical Engineering and Technology Incubation Center at IIT Bombay, with 7 other institutions, engineering as well as medical across Maharashtra, who are now developing many more different types of medical devices, affordable, reliable, suitable for the local population.
But now we have at least reached the stage of clinical trial, and hopefully in another couple of years we would have these implants functioning well into our patients. And I want to see the day where I choose an Indian implant not because it is cheap, but because it's the best implant in the world.
And this is an example how we can bring together the exceptional capabilities that exist in different organizations, but they are complementary to one another. And if you synergize them, and then of course you are able to make world-class products.
Hope you like the movie. A lot of questions in your minds. Can I have 1 or 2 questions so I know where you are thinking?
Sir, it is made for children. So, and you're telling the life is 10 years. So, as they grow, how does it?
What happens to them? Okay, excellent.
So, the dimensions, are they standard or is like for every patient?
Good, I'll answer that.
We've also seen the movement testing of the knee, but a knee also goes through impacts on jumps and walking every day.
Yes.
That wasn't really apparent.
Yeah, I'll answer that also. Alright, so that was the trailer of the movie, as you can see, and what I'll do is to more like fill in the dots, fill in the gaps, and tell you a little bit more about what happened, how it happened, who did what, when, where, and so on. There are 2 implants which you can see in the picture. There's a big difference between the 2. Okay, the first one is an imported implant, and it's about 4.8 lakh rupees, as you can see. The second is one which we developed in this project. Okay, 1/4 the cost, but between them is a long story of about 13-14 years. And the first picture which you see is an actual surgery happening for a boy, about 12-13-year-old boy, who had bone cancer around the knee joint. Instead of amputating the leg, they open the leg, remove the knee joint along with part of the bone and replace that with a mechanical joint. Okay. So this is what happens. So the picture which you see is the bone which is removed, right? You're cutting the part of the bone and removing the out. This part is the tumor part. And if you don't remove the bone along with the tumor is going to spread through the body and metastasize, and then eventually all organs will be taken over by cancer. And then when you remove the bone along with the tumor, you have a large gap left. That gap has to be filled back. That is why it's called as a mega prosthesis. Unlike you have what's called arthritic knee joints which our grandparents get, which is just like a lining on the knee joint. This is like removing the knee joint and part of the bone, so you're replacing that with a large joint. That is why it's called as mega prosthesis. So this Dr. Manish Agrawal, he was at that point at Tata Memorial Hospital, which is the largest cancer hospitals in Asia. So he would see these imported joints and then see they were very expensive. So he went to some local manufacturers who start manufacturing a very simple version of the whole thing. But with those cheap joints, he started benefiting a lot of patients who were otherwise very poor to afford the imported knee joint. If you can see this girl walking, you can't even make out which leg that she got the operation done on. Okay? It's so very natural. She wanted to become a model. Eventually she became an air hostess. And as air hostess, do you know, they do all kinds of juggleries. And you come out in a very high speed and to immediately stand up and so on, the high loads on the knee joint, natural or artificial, it has to take care of that. So this doctor started going to these local manufacturers, started implanting those joints into the patients, very low cost, hardly used to cost about 30 to 40,000 rupees. And slowly started improving the joints also. So patients were benefiting, joints were improving, but only after some time you start getting some problems. First, accolades. So newspapers said, okay, something great is happening. And this boy, for example, not only topped his class in some categories and so on, he wanted to become a doctor eventually. Okay. But on the other hand, slowly over a period of 2, 3, 4, 5 years, failures started happening. So when he talked about failures, and then I met him after the conference, he said, these are breaking or these are loosening. Okay. You can see the X-ray picture also, the stem is breaking. Okay. Or this is what is called as metallosis, where because of the not a great bio-friendly material, use some stainless steel is bio-inert but not necessarily bio-friendly. Okay. So eventually if you don't use the right composition materials, your blood can get poisoned and eventually infection, and this will actually need amputation of the leg. There is nothing you can do about it afterwards. He also met Dr. Chidambaram in a conference, who was the principal scientific advisor to Government of India, and Dr. Chidambaram said, why don't you come and talk to me and explain to me what you really need to do. So I first of all saw the surgery more carefully, understood the problem firsthand. Okay. Then we all met Dr. Chidambaram and he said, okay, I'll give you some funding to do some indigenous development of this prosthetic implant. Okay. So we started it off. It was a generous funding of about 5 crore rupees in 2006, 2007 we started, and we said we will develop this tumor knee prosthesis for children affected by bone cancer. And we also said we'll create a novel kind of a design. We'll use biocompatible materials. We said we'll test the joints before putting into patients. Okay. We also said we will create instruments to do the surgery properly, and maybe we'll also try to do a software development to plan the surgery in advance. In other words, not just one product but also the entire system of things which you need to make sure the product actually goes into the patient successfully. Of course, we never promised that it will actually go into patients. We said we will develop everything necessary to do that. Okay. So one of the questions was that is it suitable for Indian patients? Because imported joints are made for those countries' patients, usually Americans, Caucasian males and females and so on. So we went ahead and measured the dimensions on X-rays of hundreds of Indian patients to get to know what are our sizes, our standard sizes, and then you cluster it to create a small, medium, large size. Otherwise, American small size is equal to our medium size, but again then the shape is not correct. You take that small and keep our medium, it somewhere overhangs, somewhere it underhangs, and there is a problem with that. So we created the size and shape which is suitable for Indian population. Then we also said it has to mimic the natural movement of the knee joint. Natural knee joint just doesn't move like this. It is also a slight twist in other direction, which prevents it from having shear stresses. So we put this extra rotation into the whole thing. Also, we didn't want to copy the imported joints. So we created our own methods of giving those movements. So it can be patented. Otherwise, you can't patent it. You can't copy something which is already patented by other countries. We built the aluminum models. We eventually had a 3D printer, so we built a 3D printed models in plastic. Every time you print a model, go back to the doctor, show it to him, he'll make it move up and down. He say, okay, this shape is not correct, maybe do like that, maybe this size is not correct, do like that, this movement is not too much or too little. So every time you give a suggestion, you go back to drawing board, modify that, create another model, go back to him. Do you have any clue how many times we made the modifications and build the models? It was 50 to 80. Eventually it became almost 80 to 90 changes. Okay, but every change, is very painful. And doctors, what is that? They'll say, this is slightly more curved it should be. But the thing takes hours to change model on CAD and then maybe days to manufacture on a CNC machine. So we started taking signatures from him saying, okay, are you saying it is final from your side? It was a lot of fun, of course, we had, but also a lot of pain we had in this project. Now, eventually what happens is you can't make a standard joint for every patient because every patient's size and shape is different, but also tumor is different and tumor location is different. So you need different processes, shapes entirely for different patients. But then if you make a specific joint only for that patient, it will take you days to manufacture, design and manufacture. I don't even know if it is safe or not. So we can't do that either. So we took a middle path. We said we will make what is called as a modular joint. A joint which has small, medium, large size of, let us say, the condyle, the middle large part. We'll have different diameters of the axils or the stems which goes into the bone at the end. And it's all mix and match. You can take a large condyle and a small stem or a small diameter stem and you can put mix and match. So you can literally have tens of thousands of combinations of whichever patient is there. I can always build something that will fit his size and shape. Then we went to the manufacturing partner, which is NFTDC in Hyderabad. The director of that, Dr. K. Bala Subramaniam, he came forward, said, we will give you all our resources, team and knowledge and experience and of course machinery and equipment, and they put new equipment for manufacturing these designs. So we had CNC machines, we had robotic polishing machines to polish the thing to mirror finish, because when you have movement, metal to metal movement, you want mirror finish. Then you have minimum friction, minimum wear and tear. And then eventually we produce the first batch of those joints, small, medium, large and different diameters. You can see the whole thing has about 10, 11 parts which you can mix and match. Okay, the first batch came out, it was a big landmark for us. It took us about 4 years, 3 to 4 years before we got the first batch out. Now, we can't put it to patients unless we are sure about its safety. So first what we did was to prove the safety on the computer itself, virtual testing. So you can do what's called as a FEA, finite element analysis. You can put virtual loads onto that and you get a color plot. Red is high stress and blue is low stress. So you can add material at high stress and remove material at low stress. So you can optimize the size and shape. So it is low weight as well as it can take high stresses. It's about a kg in weight. And then you need physical testing because doctors do not believe in pretty pictures produced on computers. They say, show me physical proof that it is safe. So you load the thing on a what's called as a UTM, universal testing machine. Put the actual load onto that, okay, and then see that it is not failing or breaking and so on. But doctors are still not happy because you're putting a static load. What we want is when patient is actually walking and jumping and things like that. Let's say that your weight is 60 kgs. So each leg, you would think that the load taken by the leg, by the joint is 30 kgs. It is not so. The dynamic load on a knee joint during walking is 2.6 times the body weight, which means if you have 60 kg weight, each leg takes 60 plus 60 plus 30, something like 150, 160 kg weight. Okay, that is during normal walking. If you are doing jumping or things like that, it can go up to 8 times. Stair climbing is, for example, 5 to 6 times body weight. Jumping can go up to 8 to 10 times body weight. So take care of your knees. You can punish them now, but you will pay a price when you are old. Okay. So we build these machines to simulate the dynamics movement of the knee joint. And then typically we walk for about 1 million, which is 10 lakh cycles per year. You want the joint to last for a few years, but then testing itself takes a lot of time. Even if you accelerate the testing and make every movement in about 2 seconds, one cycle in 2 seconds, it will take you 4 to 6 months to reach maybe 2 to 3 million cycles. It will take you 1 to 2 years to cross maybe 4 to 5 million cycles. Okay, so it takes a lot of time test. Our problem was that the machine itself started failing before the joint failed. Okay, so we built another generation of the machines. This was built by NFTDC. They made a simpler but more robust machine, and on this machine, our joints eventually went for 10 million cycles, which is 1 crore, which is equivalent to 10 years of walking. So if something doesn't fail for 10 years, they know it is reasonably safe. Each cycle is about 2 seconds. So if you calculate, and of course you need to give some rest, you need to take it out after maybe 1,000 cycles, 10,000 cycles, do some measurements, put under a microscope and see that it is not worn out and so on. So for us to reach that 1 crore cycles took us 4 years time.
Sir, you said there could be many combinations of all the parts molecules. At that time, did you test all of those combinations?
Great question. Did you test all the combinations of all the sizes? Okay. No, it's not possible because again not enough time is there. You test the worst combination, which is typically the smallest sizes, because small sizes, if you put the same amount of load, punishing load, it will break easily. If the small one is safe, you can assume that the larger one will automatically be safe. That's strategy which we follow. So this one which you show picture here, it's a polymer part. I didn't mention to you the material of the joint, so let me tell that now. So stainless steel is bio-inert, okay? It's neither friendly nor is enemy. But you want a bio-friendly material, it is titanium. Titanium, if you make it the right surface finish, the bone literally grows onto the titanium parts and can grip it very nicely. So the stem portion which goes into the bone, onto the joint, yeah. Not completely because you never replace the joint, but it will now get onto the stem and grip it very nicely so it won't fail so easily. So titanium stems we use, but titanium is very poor in wear. You have moving part. When you are moving part, you have wear. So where you have wear, you can't put titanium. So what we do there is put a cobalt chromium molybdenum alloy, which is a very strong, very highly wear resistant material, but much more heavier than titanium. But fortunately, that doesn't go into the bone. Titanium goes into the bone. So we use cobalt chromium moly alloy for where the movement is there. Okay. But even if you make the cobalt chromium alloy for mirror finish, which is under sub-micron finish, you can see your face into that. Even if you do that, still nothing is like a flat surface, right? If you undergo in a microscope. So you don't want even that chance of wear and tear. So you put a polymer between the two metal parts. This is not ordinary polymer. It is ultra high molecular weight polyethylene, very dense material. And when you put polymer in between, so polymer is there, other side you have cobalt chromium part, other below also a cobalt chromium part is there, okay, and that movement has very low coefficient of friction, so you can go for a long time. That's the whole point. So what you see here is, for example, the wear and tear after of maybe more than 1 million cycles. Very little wear and tear. In fact, it becomes very smooth. It becomes more smooth after some movement. And of course, we made sure that the loads are not too much on the poly. A lot of small things have been taken care in the design. Now that is about the joint, but then you also need instruments to put the joint accurately in the human body. Joint may be great, but the surgery is not done properly and the whole thing fails. Finally, engineers will get blamed. Remember that. So you want to make sure that the surgery is done properly, for which you want to do an accurate cut of the tumor and also where the joint is going to enter the bone. For example, this surface has to be perfectly perpendicular to the bone canal. Bone canal is a hole in the bone. If the surface and the canal are not perpendicular, you will not get a proper biomechanical axis. You will make out the moment a person walks that he's walking a little bit wobbly, not in a natural way. So you have to get this right. So we created instruments to make sure that the cuts are perfectly done. So this is of course for a joint for put in the kid's thing, but if kid is continuing to grow and grows drastically, there are 2-3 solutions for that. One is that if he grows, let us say by 1 or 2 centimeters, you can always accommodate that by putting a more heel in the shoe. That's simpler solution. A more drastic solution is that if he grows beyond, let's say 1 inch or 2 inches and shoe adjustment is not good enough, you will have to take the thing out and put a bigger one, which is a very drastic solution. Okay, but there is a third solution which is there, which is that you put one component in the entire joint which has a worm gear mechanism, and you can either put a screw from outside, just a screw only, not take the entire joint out, and you can turn the screw and it kind of expands, expandable processes. But still you need to put a screw inside the body, and wherever you enter the human body, there is always a chance for infection. So other way to do that is to create something. It has a magnetic coil, or let's say something which responds to magnetic coil. You put a leg in a magnetic coil, turn the coil on, the coil rotates, magnetic field rotates, and then this inside some nut or bolt will rotate, and you can slowly lengthen that. And if you lengthen too much, you can always do the reverse turning of the whole thing. But these joints are very expensive. They are like 15 to 20 lakh rupees, 25 lakh rupees. Okay, and not only that, even there is a limit of how much you can expand. It's again about an inch or so. But at least it maybe instead of 3 surgeries, maybe you can now do 2 surgeries. But this is an issue, and you cannot solve the problem.